Hello, welcome to our tutorial on short learning. I am Sanghyuk from Naver AI Lab. This tutorial is a joint work with Kyungwoo from University of Seoul and Yonghan Jung from Purdue University. Our tutorial consists of 4 parts: introduction to short learning, understanding short learning through the lens of causality and invariance, learning invariant representations, and how to mitigate short learning in practice. You can find the detailed technical report for this tutorial in our homepage. Now I am going to start from the first part, introduction to short learning. Machine learning opens a new stage of automation as well as new applications. For example, these images are examples of computer vision applications based on machine learning, such as pose estimation, object detection, and face recognition. Another example is self-driving cars with line tracing and semantic segmentation. However, machine learning models cannot understand the problem itself. For example, as shown in this video, we can make a semantically meaningless image patch which fools the object detector. As this guy brings the patch to the another guy, the detector is fed to detect person class. It means that the object detector makes decisions not only focusing on person objects, but it also attends on other undesired features. Here is another interesting example. In this video, the self-driving car thinks Burger King sign is a stop sign. So this car is going to stop in front of the Burger King sign. It means that the object recognition module of the self-driving car does not actually understand what does stop sign mean. What does stop in the stop sign mean? But just focusing on the overall appearance of stop signs. Why that happens? There could be a lot of interpretation of this phenomena. But in this tutorial, we are focusing on the short learning problem. What is short learning? Machine learning models often rely on easy-to-learn shortcuts without understanding the problem itself. For example, the goal of visual question answering model is to answer a question related to the given image. For example, here, what color is banana? We human know that the left one is yellow and the right one is green. However, because bananas are typically yellow, VQA models often answer the question without looking at the image, but just answer, this is yellow. This is not what we want. This example shows when a model does not make a decision based on desired features, but undesired features, like ignoring the images when answering the question. In this case, we say there exists short learning. There are also a lot of examples of short learning in many applications. For example, an image captioning model describes this hillside image as a grazing strip because in the training dataset, most of green hillside images containing grazing strip and most of captions describing grazing strip instead of green hillsides. You can find more interesting examples in this reference paper. Let's see more human-related example. This is an automatic job interview case. Here, a machine determines 5 criteria of an interviewee to determine whether to hire the interviewee or not. Our question is the machine truly focusing on how the interviewee answers the question, where the machine attends on the other something? This study investigates the question by hiring a professional actress and letting she acts on interview with a fixed script. If the machine truly understands how the interview answers, then the machine will not change its prediction by different appearances when the script is the same. Well, however, we can see that even if the actress acts the same script and the same action, the machine predictions vary a lot by different appearances like glasses or headscarf. Do you think a person wearing a headscarf is more open than a person wearing glass? It is not just problem of fashion. This machine also varies a lot with different backgrounds. Do you think it is fair to predict the interview is more extrovert when a picture or bookshelf is in the background? Do you think now I become more neurotic? No, it is not true, right? It even happens for different brightness setting of camera. we can think that the machine learns something undesired one, at least for the job interview case. Okay, to understand why short-term learning happens, let's briefly recall the basic of machine learning. A machine learning model is trained with data X and label Y. If the machine predicts wrong prediction, then we update the model to make the correct prediction. If the prediction is correct, then we don't update the model. It is the high-level description of how a model learns from data. Remember, the model is not updated if the prediction is correct. When does short-term learning happen? Assume a toy scenario of classify car or boat. Cars are on roads, boats are on water. So a model can make perfect predictions without looking at car or boat, but focusing on background. When a car is on water and our boat is on road, the model will make wrong prediction because it attends on backgrounds. In this example, the model can perfectly solve the given problem by only attending on easy shortcut features like water pattern without actual understanding of problem. Because the prediction is correct, even if the machine makes a decision based on undesired features, the model will not be updated. Okay, let's make the example more simpler to understand short-term learning more deeply. We are interested in which feature is selected by a model, desired one or undesired one. To make the question, let's assume a toy example when every sample with class 1 is a small red circle, and every sample with class 2 is a medium green triangle, and every sample with class 3 is a large blue sphere. Now, what is the class of a small blue triangle? If the model focuses on shape, then the prediction will be 2, triangle. If the model focuses on color, then the prediction will be 3, blue. Using this simple test case, we can examine which feature is actually preferred by machine learning models. When we test this scenario, machine learning models show very strong preferences on specific features. Especially, we can see that regardless of architecture choice, models prefer to recognize objects by color. So if color is our desired feature, then there is no short-term learning. However, when color is undesired features, then short-term learning happens. In other words, short-term learning problem is depending on how we define a task and desired feature. When the machine preference and the desired feature is not aligned, then naive learning strategy will lead to short-term learning. Therefore, we need to consider something more to avoid short-term learning. Now, it is time to finalize part 1. I introduced short-term learning problem when a model makes a decision based on undesired feature, not desired feature. I showed examples of short-term learning, such as automatic job interview. I also showed that a machine can be biased to the easy-to-learn shortcut if our target task and desired feature is not the same as the easy-to-learn shortcut. Okay, now Yonghan will introduce a lens of causality to understand short-term learning better.
Hello, my name is Yonghan Jung, and today I'm going to present the topic on understanding short-term learning through the lens of causality and invariance. Short-term learning bias happens in practice. For example, consider the task of classifying images of boat and car. So specifically, we have a data, which is a boat in the water and car on the road. And our machine learning model will learn a decision rule for classifying boat and car. And given a new set of images, which is that boat in the water, machine learning model will classify this as a boat. However, as we see from the previous part, modern machine learning models oftentimes make a mistake. For example, if the image is that the boat is on the road, then the machine learning model can make a mistake by classifying this as a car. So what's going on here? And this happens because the machine learning model used unintended, undesired feature as a decision rule. For example, given the set of data, machine learning model trained in the way that it will determine the image as a boat if it has a water background, and it classifies the picture as a car if it has a road background. And this way of training actually works pretty well for the training data set. However, when there is an unseen new image comes in, like boat on the road, because there is a road background, machine learning model will wrongly classify this as a car. So this gives a definition of short learning bias. Short learning bias is a phenomenon where the machine learning model failed to generalize for a new set of samples because of unintended, undesired feature called shortcut in establishing decision rule. So in this part, we will study the short learning bias problem. Specifically, we will provide a formal understanding of short learning bias through causality. And we will propose two approaches for preventing short learning bias, which both suggest that causal features should be used for constructing the machine learning model. And two approaches are the following. The first approach is to avoid causally irrelevant features to the true label as much as possible. And the second approach is that we have to find the machine learning model that works best for all heterogeneous data generating processes. And finally, we will provide a principle for identifying causal features by leveraging the causal invariance property. So let's cover the first topic, formal understanding of short learning bias. We first note that data generating process can be expressed as functions. For example, consider this data and the label. Our data generating process is composed of multiple functions. For example, we assume that there is a function that generates a background object, and there is a function that generates a target object, and there is a function that generates a label. And this view can be formalized in terms of something called structural causal model. Structural causal model is formally defined as a tuple having the set of observed variable, set of latent variables, and set of functions that determining the value of the VI and the probability distribution over latent variables. And here is an example that how the SCM can be used for describing the data generating process. So we have a structural causal model for the background, target, label, and the distribution over variables. Then this structural causal model generates the data. And one thing that we want to note is that instead of having the access to the structural causal model, we have a qualitative description which can describe the structural causal model. And one of the power of the structural causal model is that it can encode the intervention on data generating process. For example, from the previous data generating process, suppose instead of the function that generates a background, suppose we intervene on that function and enforce that the background should be road. Then by this intervention, it generates the image like that, which is that the boat is the same as previous, but now the background is the road. And this intervention is graphically encoded in the way that all the edges to the background variable is coded, and it is replaced to the value road. And this intervention is encoded by the structural causal model in the name of something called sum model. So sum model is a structural causal model induced by the intervention. And given the SCM and the sum model, MVI is the structural causal model by replacing the function that determines the value of the VI to the fixed constant, roughly speaking, in the data generating process, it's just a fix the VI as a constant small VI. And we'll define the environment as a set of structural causal models and the sum models. And what we have seen is that in the previous example, the image, both in the water and the boat on the road, they can be both generated from the structural causal model. So this environment, which is a set of the structural causal model and the set of the sum models, they are data generating process. So with these notations, we can formally define the problem as follows. Our task is to construct a performant machine learning model that working well for all environments. Specifically, for multiple environments which generates the samples, our goal is to construct a machine learning model from this sample that works for all environments for unseen images or unseen data. Now we move to the next section for discussing then how do we construct the machine learning model for preventing the shotgun learning bias. So we first discussed our first approach. To go deeper to the first approach, we first consider how humans classify. So there is a boat in the road, and what humans see is the boat object and the water object. And only this boat object affects to human decision, like even for a baby. So to witness this more specifically, consider this image that the boat is now on the road. And there is a boat image and road image in this picture. And human can still classify this image as a boat because this human only uses boat object to classify. And this is true because I have a 3-year-old boy, and I mean my son. So I test this with my son, and my son successfully classified these two objects. So the thing that I want to say is this: humans don't use background objects for classification. And what about the machine learning models that is contaminated by shotgun learning bias? As we described in the previous pages, machine learning model contaminated by the shortcut, they use the unintended features. In here, unintended feature is the water and the road. And because they use the unintended feature, the machine learning models are making mistakes by classifying this object as a car because they use this road object. Or in other words, these objects which doesn't causes humans label, machine learning models use this label which is causally irrelevant to humans label and make a mistake. So this actually relates the shotgun learning bias and causally irrelevant features. That is, previously the shotgun learning bias was defined as a machine learning model failure due to the usage of unintended and undesired feature. And now we can actually rewrite this as follows: that machine learning model fails due to the use of causally irrelevant features. So this gives the first approach, which is that we have to construct the models by avoiding causally irrelevant features as much as possible. Now, we formally define the causal irrelevance. A set of variable x is said to be causally irrelevant given other intervention if intervening on x does not affect y. And formally speaking, in probabilistic sense, intervening do x and intervening on do x, which is that these two values are different, doesn't affect the y in probabilistic sense if we have an intervention of w. And we can also define, and we actually extend this definition by the case that by not considering this other variable w, that the set of variable wx is said to be causally irrelevant if intervening on x doesn't affect much if we have an intervention on the rest of the variable. For example, intervening on x doesn't affect much in probabilistic sense given other intervention on the rest of the variable. And this causal irrelevant set has a really interesting interpretation in terms of the graph. To say this, we have to first describe the causal feature. For the true label y, we say this PAY, abbreviation of parents of y, is something called causal feature if it's a parental set in the graph or direct cause in the graph. And one graphical interpretation of the causal invariance set is some set of the variable is causally irrelevant set if it does not contain any variable in the causal features. So let's go back to our example. In here, this water background is causally irrelevant because it's not the direct cause of the true label. In the same sense, this road is also causally irrelevant set because it's not the parent of the true label. And this is how humans make a classification, and approach one says that we should avoid to use this kind of the causally irrelevant set. So this means that approach one basically states that machine learning models decision rule should mimic humans' decision rule. So here are some formal interpretation of the approach one, which states that we have to avoid causally irrelevant features as much as possible. So formal interpretation is that, first of all, we want to mention that the largest causal irrelevant set is a V minus PAY, which is that all variable except causal variable. And approach one says that we have to avoid causally irrelevant set, means that we have to avoid V minus PA, meaning we have to use causal feature PAY to construct a model for preventing the shortcut learning bias. Let me repeat. We have to avoid largest causal invariance set, which is a V minus PA. That means that we have to use causal feature PAY to prevent shortcut learning bias. Now, okay, this was our first approach, and now we will go to the second approach, which is that finding a machine learning model that works best for all heterogeneous data generating process. So we first recap our problem setup. Our task is to construct a performant machine learning model that working well for all environments. And our approach two says that this is a task that we have to minimize the error of the machine learning model, even in the worst environment. So approach two is that we have to find the machine learning model that working well, even in the worst environment. So here's some formalization in math. So this FV is a machine learning model, and Y is a label, and this L is a prediction loss, and this is the expectation over P. So this is the expected prediction error of the machine learning model F for the true label. And approach two says that we have to find a model that working well for worst environment. And the worst environment is defined in the sense that for all environment and all distribution that is given in the environment, which was a structure causal model, and there are some models, we will find worst environment is the environment that maximizes the prediction error. And our goal is to minimize the prediction error even in this worst environment. That is, we want to minimize the expected error of the machine learning model even in the worst environment that maximizes the expected error. And here's some interesting research that prediction models with causal features is the most performant one. Specifically, this is the math problem that we want to solve for approach 2. And it says that if the error is given as a mean square error, which is pretty commonly used in loss function for the regression problem, the solution is the expectation y given PAY, which is a relation between the true label and causal feature. Also, if the loss function is given as a classification error, then the solution is given as a probability of the y given causal feature, which is the relation between the true label and causal feature. So the takeaway is that most performant model working for all environments, it can be found by constructing the model with causal features. So, or in other words, to prevent the short-term learning bias, we have to construct the model using causal features. So here are some intermediate summary. We covered the approach 1, which states that we have to avoid causally irrelevant features as much as possible. And the second approach is that we have to find the performant model working for all environments. And we show that these two approaches are reduced to find the causal features and make the machine learning model with these causal features. All right, now we will cover how to identify this causal feature. We first note that identification of this causal feature is difficult. That's because this causal feature is a PAY, parental node of the y, but without the graph, identifying PAY is quite hard. So how can we identify this PAY or causal features? So to identify, we first study the property of the causal feature called causal invariance. And causal invariance is a property that even if there are a lot of the environment, the relation between the true label and the causal feature, they are the same. For example, by manipulating the data, we can generate the image, which is that boat in the water, or boat in the road, or boat on the forest, boat on the space. We can make a lot of the perturbed examples of the boat. But the relation between that boat object and the true label, they remain the same. And formally speaking, this is the probabilistic relation between the label and causal feature is invariant, or for all structural causal model, the probabilistic relation between PY given causal feature are the same. So we will use this causal invariance to identify causal feature. We first observe that finding the set X is much easier than finding the causal features. For example, if we have some good conditional probability estimator, we can find the set that invariant to Y by checking this for all environments. Or if we have a good conditional independence measure, we can check that Y and V minus X are independent given X or not. And if it's conditionally independent, then we can consider X as an invariant set. So we define this as a test function, that the test function tests whether or not this X is invariant to Y for all environment. And with this test function, we can identify the causal feature as follows. We first note that the causal feature is the smallest set that passing this test, meaning causal features is the smallest invariant set. So if there is a test that can capture the invariant set in high probability, the smallest set passing this test is highly likely the causal feature. So if we have a high probability test function that can capture the invariant set, then smallest invariant set with this test function is highly likely the causal feature. Okay, so far what we discussed is that two approaches, which is to avoid the causally irrelevant features and find the most performant model for all environments. And these two approaches are reduced to find the causal features and use this to construct a machine learning model. And our last result states that in smallest invariant features is highly likely the causal features. So to prevent the short learning bias, we have to use the smallest invariant set and construct a machine learning model with these features. So here are the summary. We formalize the problem of learning the machine learning model robust to short learning bias with structure causal model. And we propose two approaches which have the same conclusion, that construct a model with causal features. Finally, we discuss that how to use a causal invariance property to identify causal features. So thank you very much for listening.
Hello, my name is Kyungwoo from University of Seoul. In this talk, I will give a presentation on learning invariant representations. First of all, we will review the invariant features to get a competitive performance for all environments, including the most disadvantaged environments. Constructing the invariant features is important. We will denote the invariant features as PAY, the parent of Y. Let's see the table data example. We bring the example from the adult dataset, the benchmark dataset for fairness. What we want is to determine whether a person makes over $50,000 or not. Besides, we will assume that the occupation and hours per week are the parents of Y, the invariant features. On the table dataset, we just utilize PAY as an input feature if we know the PAY. Then the model can predict Y well based on the invariant features. Besides the tabular dataset, we will see the image and text dataset example. You will already be familiar with the car and boat example. The first example is to predict whether the image is about a car or boat. The object, not the background. The second example is to predict whether the person's hair is blonde or black. The third example is to predict whether the two sentences have an intermental relationship or a contradiction relationship. From now on, we will see each example in detail. The left figure denotes the training dataset. If we collect the dataset without any consideration, the background of most car photos is a road. Similarly, the background of most boat photos is water. In this case, the machine might focus on the background because the background is distinct features, and it is enough to minimize the training loss. In short, the machine might learn the non-invariant features, the background. It will cause a problem when we encounter the new image on test time. The machine will determine the right image as a car because the background is road. We can observe a similar phenomenon in the second example. We bring the image from the Celeb A dataset, one of the benchmark datasets. In the dataset, most females have blonde hair, while the males have black hair. In that case, it is enough that the machine focus only on the male or female to predict the hair color. Similar to the first example, the machine will determine the right test image as black hair because the image is for a male. In short, the machine does not learn invariant features, but learn undesirable features such as gender. The problem is not limited to the image example. We bring the sentence from the MNLI dataset, one of the benchmark datasets for NLP. The task of MNLI is to predict whether two sentences have a contradiction relationship or intermod relationship. Among the dataset, most contradicted sentences have negation expression. Therefore, the machine is enough to learn the correlation between negation and contradiction. However, it is not an invariant feature, and it may cause the performance degrade. When the machine encounters the test case such as the little girl is sad and the girl is not happy, the machine will predict that they are contradiction because of a negation expression. In short, what we want is invariant features. How can a machine focus on the invariant features? The simplest idea is that injecting the invariant features only into the machine. As you remember, it is relatively simple for a tabular dataset. If we know the invariant features, parent of y, we just inject that column features only into the machine. What about an image? Can we inject the invariant features only into the machine easily? Let's see the image case in detail. In the left case, the invariant feature is the object, not the background. However, it is not trivial to extract the invariant features only in the raw image. In the right case, the invariant feature is the digit, not the rotation angle. Similarly, it's not trivial to extract the digit features only without rotation angle and the thickness features. They cannot be separated easily. To recap, injecting the invariant features only into the machine is not trivial for image dataset. Therefore, we usually inject all images into the machine. When you train the image, we usually adopt a neural network-based feature extractor and classifier. We expect and wish that the extracted features H include the invariant features, such as object only. However, in reality, the H might include undesirable features such as the background. It may cause a problem when the machine encounters the image such as a boat on the road. When the extracted features include undesirable features, it might cause a problem. How can you encourage the extracted features only focus on the invariant features, such as the object, not the background? What we want is that H includes the both for boat and water image, and boat on the road image also. To learn the invariant features, the most intuitive approach is a general data augmentation. Let's assume that we only have that kind of images, such as boat on the water and the car on the road. When we train our machine on the training dataset only, it will cause the problem as the previous. What if we can train more diverse datasets, such as a boat on the road and a car on the water? Our machine is able to know that the background does not indicate the label directly. Therefore, our machine starts to focus on the object itself, the invariant features. In summary, the first strategy is to augment the dataset and train the machine on the augmented dataset also. Let's think about the problem in detail. Can we generate the image such as a car on the water and the boat on the road easily? It is not trivial to generate that kind of image based on the boat on the water and the car on the road image. In other words, suitable data augmentation is not trivial. Then, how can you achieve invariant feature learning? Another approach is to regularize the extracted features H1 and H2. Let's assume that we have two environments, both on the water dataset and both on the road dataset. What we want is to make extracted features H include the invariant features, the shared features across the environment. In this case, we regularize the extracted features H to focus on the both object, the invariant features. We summarize the problem cases and their approaches. The first case assumes that we can augment the dataset to generate a diverse environmental dataset. The second case alleviates the data augmentation assumption. When the augmentation is not trivial, we can utilize the regularization base to learn the shared features across the environment. Lastly, the third case assumes that we do not utilize the environment information as well as the data augmentation. From now on, we will cover each problem case and its detailed solution approach. We will cover the first case that the data augmentation is possible. In this case, we bring the rotated MNIST dataset. Let's assume that we have non-rotated 0 and rotated 8 in the training dataset. The task is to predict the digit number, 0 or 8. And the rotation angle does not cause the label. Therefore, we want the machine to learn the invariant features, the digit, not the rotation angle. We will rotate the given image to learn the digit information, not the rotation angle. For the given digit 0 image, we generate a diverse augmented dataset such as a 15-degree rotated 0. After we generate the augmented dataset, we let the machine learn the original image and the augmented images also. After that, we will introduce some constraints to extract invariant features. The first approach is to match the output of the machine. We restrict that the output of the original image and rotated images are the same. Because of the output restrictions, the machine produces the same output, whether the images are rotated or not. The second approach is to restrict the extracted representation, not output. Representation invariance constraint encourage that the representation attend to the shared features, the digit in this case. For the generative model, such as the variational autoencoder, we can interpret the representation restriction as a posterior restriction. Representation constraint might work better than output constraint on the generative models. Another approach is to average the output. We utilize the average of the model's output as our prediction. In that case, the machine produces the same output, whether the images are rotated or not. Until now, we have handled the case 1 situation, where data augmentation is possible. Let's imagine the more realistic settings. Even though we can augment the data set, such as rotation, the optimal rotation angle might be unknown. We know that the suitable rotation angle for digit 6 is from -90 degrees to +90 degrees. When we rotate the digit 6 image 180 degrees, the image is transformed to digit 9, not 6. How can we let the machine know the optimal data augmentation policy automatically? There is a way to learn the suitable data augmentation policy itself. For the rotated MNIST dataset, we let the rotation angle zeta as a learnable parameters. The objective function of this method has two components. The first one is the classification loss. It makes the machine minimize the training loss whether the images are rotated or not. Second, the regularization loss to avoid the rotation angle parameter zeta degrade to 0. When the rotation angle parameter zeta is learned as 0, the regularization loss will be high. On the other hand, the training classification loss becomes large when the rotation angle parameter zeta has an unusually large value. If the zeta is learned as 180 degrees, the image is changed to 9, but the label is still 6. Therefore, the classification loss becomes large, and we can get the appropriate rotation angle automatically by minimizing the objective function. From now on, we will see the case 2, when the suitable data augmentation is not trivial. Given the boat on the water dataset, augmenting it to the car on the water dataset is difficult. We need different approaches instead of data augmentation. To get a high-level idea, let's assume that we can train each environment independently. The first environment is boat on the water, and the second environment is boat on the road. There are 2x2 cases whether the first or the second feature extractor learns boat or water. The ideal case is that both feature extractors attend to the boat object, not the background. In that case, the optimal classifier W1 and W2 are the same because they need to classify the boat object as the boat. The natural question is, what if the optimal classifier for each environment are the same? when the optimal classifier should be the same across the environment, the feature extractor should attend to the both image. Whether the images are the boat on the water or the boat on the road. In short, making optimal classifiers are the same across the environment, the machine can learn the invariant features. Therefore, the IRM introduced the following constraint optimization problem. IRM constrained that the optimal classifier across the environment are the same. Besides, IRM minimized all the environment transitional training loss. The constraint problem requires a complex multiple optimization problem. We can approximate the optimization problem as follows. The approximated IRM combines the transitional training loss and the gradient regularization loss. Minimizing the gradient of the loss with respect to the classifier indicates the minimization of the classifier sensitivity across the environment. It indicates that the minimization of the classifier sensitivity across the environment. It induced the same optimal classifier across the environment. Another approach for invariant representation learning is to focus on the disadvantaged environment. Our usual training dataset might contain more environment 1 dataset, both on the water, than the environment 2 dataset, both on the road. Therefore, the machine will attend to environment 1 to reduce the average training loss. As you will see earlier, then the machine will focus on the background, not the both object. How can you alleviate the problems? One of the solutions is to focus on the disadvantaged environment first. When we let the machine focus on the disadvantaged environment, it will focus on the invariant features, the both object. Let's assume that the machine focused on the road background to infer the boat label. Then the machine will have a low training loss in environment 2. However, the machine will have high training loss in environment 1 because there is no relationship between the road and the boat. It is noted that the number of data in environment 1 is larger than that of environment 2. And the average training loss will be high. Therefore, the machine tries to focus on the boat object itself when we make the machine attend to the disadvantaged environment first. In short, training the disadvantaged environment mostly is helpful for invariant representation learning. We can formulate the idea as follows. Until now, we introduced the IRM and group dialog. The major concept of IRM and group dialog is reasonable. IRM encourages that all environments share the same optimal classifier. Group dialog attend to the disadvantaged environment. However, they still have limitations. In the case of IRM adopts the approximation technique for the bi-level optimization. And invariance on non-linear setting is not theoretically guaranteed. In the case of group dialog, it only handles the interpolation of the training environment, and it requires strong regularization. Besides, both IRM and group dialog can only access the training environment. Therefore, the superiority of IRM and group data is not guaranteed when we handle the test environment that are sufficiently different from the training environment. We can check the limitation empirically on waterfall dataset. Waterfall dataset consists with two types of background and object. Waterfall on water, landboard on water, waterboard on land, and the landboard on land. The disadvantaged environment is the anti-diagonal, waterboard on land and landboard on water. Group DRO improves the disadvantaged environment occurrence compared to the vanilla model ERM. However, the disadvantaged environment occurrence is still lower than the average occurrence. Besides, we find that the extracted features from the group DRO still contain undesirable features, background. When we classify the background based on the extracted features, it is easily classified, and it denotes that the group DRO still run the undesirable features. We can check that the IRM has a similar issue. We visualize the extracted features from ERM and IRM on the color damnedness dataset. Both features of ERM and IRM are clearly separated by undesirable features, such as background or color. The visualization denotes that the extracted features from IRM contain undesirable features. There are many recent papers that report the empirical limitations of IRM and group DRO. The domain bed is a well-known test bed for domain generalization that covers diverse datasets. And it is easy to compare the algorithm in fair experimental settings. For the domain-based dataset, IRM and group DRO show less performance than ERM, the vanilla model. The last case of the part 3 is that we do not have environment labels, as well as the optimal data augmentation policy. Introduced models in part 3, including IRM and group DRO, require the environment labels. However, the environment labels or bias labels are not always accessible. The label annotation cost is expensive, and it could have privacy issues. How can you learn the invariant features when we encounter the case 3? One of the strategies is to infer the environment labels automatically. To infer the environment, we will utilize the principle of IRM and group DRO. The principle of IRM is all environments should have the same optimal classifier for the invariant feature learning. IRM principle reduces the difference between the environment. It means that violating the principle of IRM encourages the difference between the environment. Therefore, we can infer the environment of each data instance. Similarly, we can infer the environment based on the group DRO principle. Group DRO principle is the most disadvantaged environment has the highest training loss. It denotes that each environment has a different training loss curve. Therefore, we can infer the environment based on the training loss curve. For a detailed explanation, please refer to the appendix of this slide or the following papers. In part 3, we cover the major ideas for the invariant representation learning. For the invariant representation learning, we introduced the two approaches, the data augmentation and the regularization-based approach. However, both approaches require an environment label or some specific assumption. Besides, we observe that the approach still contains undesirable features, and invariant feature learning is still a challenging problem. Because of the time limit, we have focused on some major approaches. There are diverse variant works, and we summarize the recent works. This is a reference for the part 3. Please refer to the paper for a more detailed explanation. Thank you.
Thanks, Kyung, for introducing how can we make a model with invariance. I am Sanghyuk again. In this last part, I'm going to talk about how can we mitigate short-term learning in our actual applications and what will be the future research questions of short-term learning. As Kyung introduced, we need bias labels to avoid short-term learning. Let's assume the car and boat example again. If we have bias labels like road and water, aside from the original car and boat labels, then we can make a model invariant to background by using the methods introduced by Kyungwoo. Then as Yonghan showed, we will get an unbiased model. So if we want to avoid short-term learning in our own scenario, we have to start from dataset construction. We have to consider data collection first. Data collection should be designed to avoid undesired dataset biases. For example, collecting more data samples for both on load or minority samples to prevent the learning become trivial by easy to learn shortcuts. Also, we need additional annotation process to collect bias labels, such as load water labels or sensitive attributes such as gender or ethnicity. However, it is not always easy. First, data collection itself is often non-trivial for uncommon samples. How can we gather enough images of both on loads? Similarly, it is very difficult or sometimes impossible to collect samples with every possible situation, such as boat on load, car in the sky, frog hugging bottle, or elephant with zebra skin. Even if we can collect such uncommon samples, sometimes additional annotation process itself could be very expensive. Assume we have few samples with bias labels and the other samples do not have bias labels. In this case, we can estimate bias labels using a bias label estimator trained on the biased label samples. We can train a bias label classifier using a few samples with bias labels. Then we estimate bias labels of the remaining dataset using the biased label estimator. Then we can apply the existing methods using the estimated biased labels. Of course, this approach can be limited to the quality of the biased label estimator. Sometimes bias labels are not easily determinable. For example, how can you define the bias label of the case of VQA? We only know that a model uses a text shortcut, but it is not trivial to make a bias label for this case. How can you annotate the bias label for the green banana case? How many bias cases exist? We cannot specify this. In this case, we can use the biasing methods using biased models. We assume that using the original task supervision alone will lead to a biased model. Now, assume we have a biased model and assume we can make our target model be different from the biased model. Then our target model will be less biased because we make the target model be different from the biased model. Now, there are two big questions. The first one is, how can we make biased models? And the second one is how to encode be different. We are going to show some examples of how to make biased model in this tutorial. We are not going to introduce how can we encode be different in this talk. For some specific cases, we can make a perfectly biased model by its design. In VQA problem, we know that a VQA model is biased to text. Then if we make a model only focuses on text without looking on image, then the model will be perfectly biased. Now we can make a debiased method using be different supervision between our target model and text only model. The target model will be less biased to the text modality. Another example of perfectly biased models can be found in the specific background biases in image. We can design some models with pixel level operations to make a color biased model. Then we can apply B-difference supervision using the specific designed model. However, it is not always possible to make a perfect biased model for every task, because we need a very strong domain knowledge for designing a specific biased architecture. Instead, we can use some additional knowledge if we know when a model is biased. For example, if we know that a biased model focuses on local areas than global areas, then we can make a biased model by letting a model only able to see very small local areas to make decisions. In other words, in this case, we can design intentionally biased model by an architecture design. Sometimes it is not able to find such architecture design. Instead, we can use the knowledge of when shortcut learning happens. Shortcut biases are easy to learn compared to the desired features. In this case, we can assume that a model with shorter training time already biased to the easy shortcuts. Therefore, we can assume that the early stage model is biased model and make our target model be different from the early stage model. Similar ideas can be found in noise level training methods. The debiasing with biased model strategy can be effective if we can correctly make the biased model. Here, a model is biased if we use only original task provision. However, it is debiased when we make the model be different from a biased model. To apply this method, we need to assumption on how to make debiased models. Also, we need to encode be different effectively. Now we briefly see how to make a model avoid shortcut learning in many scenarios. However, how can we know that whether my model actually avoids shortcut learning? Can we ensure that my algorithm is always debiased to other scenarios as well? Again, shortcut learning depends on how we define the task and how we build the data set. There could be many evaluation benchmarks for measuring a model learns shortcuts by different point of view. However, I am going to introduce two popular tasks to measure whether a model attends on undesired feature. These two benchmarks are the same in terms of measuring whether a model only learns easy to learn shortcuts, but they are different in terms of actual problem setting. Okay, so first one is domain generalization. This scenario measures the performance of the model even under very significant data distribution shift. If the model truly focuses on the problem itself, then it will show the same performance even under distribution shift. This is an example of domain generalization dataset. Our task is to classify dog or horse. There also exist 4 different domains: sketch, cartoon, art painting, and photo. We first train a model on the first three domains: sketch, cartoon, and art painting, and test the model on the last unseen photo domain. Unfortunately, as we can see here, in practice, a well-tuned naive learning method is often better than theoretically well-founded methods. It is aligned with Kyungwoo's last slide. We still need more improvements. Now let's see another evaluation scenario, cross-bias generalization. This task aims to evaluate a scenario when bias labels and target labels are strongly correlated. For example, when background color is strongly correlated to digit number. We aim to train a model without looking at background, but digit itself. It is different from the domain generalization task because domain generalization training set contains multiple domains and each domain and each target is not correlated. But it measures the accuracy on unseen domain. Cross-bias generalization task, cross-bias generalization evaluates when bias labels and target labels are strongly correlated. Here is another example. Gender is bias and age is target label. We can test the model by training this one on biased data set. Every female is young and every male is old. Then we can evaluate the unbiased accuracy on the unbiased data set. Unfortunately, the existing benchmarks are relatively toy scenario compared to real-world applications, because it is almost impossible to make perfectly the biased dataset even for the test set. How to make correct benchmark for short-term learning is the open question, and we have to focus on correct evaluation benchmark for making more better method. Finally, I want to re-emphasize that short-term learning is defined by humans. Who defines a feature is desired or undesired? Humans. We have to focus on not only machines and data sets, but also humans for avoiding short-term learning. We have to consider human-in-the-loop learning process or evaluation process. This is the take-home message and summarization of this tutorial. We have to consider various ways to avoid short-term learning. We have to carefully build our data set. If it is possible, we need to annotate bias labels. We have to make an algorithm be unbiased. Most of academic studies are located here. We have to build more realistic correct evaluation benchmark for short-term learning. Finally, humans should be considered in the machine learning model development pipeline itself, because short-term learning is defined by humans. This is reference of part 4. And this is the end of our tutorial. Thanks for your attention and enjoy your FAccT conference.